Welcome, students. We're going to be continuing looking at transformations of functions, but right now we're going to be focusing on transformations of quadratic functions. Now, we graphed quadratic functions before, even if we didn't know they were functions. So recall, earlier in the semester, we graphed things in the form y equals ax squared plus bx plus c. We had two lessons, the first of which we looked at how to find the x and y intercepts of the parabola, and the second one we looked to find the vertex. Now, back when we were graphing these, we didn't call them functions because we hadn't looked at functions yet. We hadn't defined what a function was. We just said that we were sketching the graph of a quadratic equation in two variables. But now what we're going to do is we're going to look at the same thing, but because we know that this is a function of x, we're going to be talking about graphing quadratic functions again. But instead of looking at them like this, we're going to be talking about how these are all transformations of the standard quadratic function f of x equals x squared. So I want to talk about how we can do this if we're given something in this form. And I have a definition that we're going to look at now. A quadratic function in the form f of x equals ax squared plus bx plus c, which is the form that we've seen them in before, can be written in the standard form of f of x equals a times x minus h squared plus k by completing the square. In this case, its vertex is h comma k. This standard form, which we'll see in just a moment, is nice because just by looking at it, we can read the coordinates of the vertex. Let's take a look at an example to see how this works. Let's consider the function g of x equals 3x squared minus 12x plus 8. What I want to do is I want to complete the square here, and then we'll be able to see what the vertex is and how this function is a transformation of the original function f of x equals x squared. So what I want to do is complete the square. This will be a little bit different than we've seen before because we have a leading coefficient, but I'm going to walk you through it so you can see exactly how it works. Now the first thing I want to do is just focus on the first two terms, and we're going to take this 8 and kind of leave it on the outside for a little bit because it's not important right away. And in these first two terms, I want to factor out the leading coefficient. In this case, that's 3. So when we factor out a 3 from the first two terms, we're left with x squared minus 4x. Now I'm going to put the closing parenthesis a little bit to the right, and then the plus 8 on the outside. And the reason I'm doing this is because now we can complete the square for this binomial. We take the negative 4 here, we divide it by 2, it's negative 2, and we square it to get positive 4. So we need to add 4 to complete the square here. But what we've really done is we've added 3 times 4, which is 12. We've added 12 to the function, which changes the function. You can't just add a number to a function and have it be the same. So to counterbalance that, on the outside, we're going to subtract 12. Because if we add 12 and then subtract 12, we're right where we started with. So this gives us an equivalent function to what we had originally. And now we can factor this perfect square trinomial. It becomes x minus 2 squared. And then on the outside, 8 minus 12 is negative 4. So we've got 3 times the quantity x minus 2 squared minus 4. And this is our function g of x. Now, we can figure out just by looking at this what the vertex is going to be. Remember, the vertex is given by h comma k. Now, h is the quantity that's being subtracted inside the parentheses. In this case, 2 is being subtracted, so 2 is the value of h. And then k is the constant term at the end. In this case, that is -4, so k is going to be -4. And so our vertex is going to be at the point 2, -4. Now, I just told you that this is the vertex. I didn't explain why it is. So what we're going to do is we're going to talk about how we can get this as a transformation of f of x equals x squared. And we're going to see that this is exactly where the vertex goes. So I want to look at f of x equals x squared. And as we've done before, I want to see what series of transformations we can make to turn this into our 3 times x minus 2 squared minus 4. Now the first thing we can do is replace x with x minus 2. And we know that when we do that, we end up having a shift to the right 2 units. Then we multiply our function by 3. So we replace our function with 3 times the function. This gives us a vertical stretch by a factor of 3. And then finally, we take the function that we have and we subtract 4 from it. We know that this is a shift down 4 units. And so we can see that our quadratic function is a transformation from the original function f of x equals x squared by shifting right 2 units, then stretching vertically by a factor of 3, and then shifting down 4 units. Now, I want to go through the process of graphing this really quickly using these transformations. So we'll start with the graph of f of x equals x squared, which we have graphed 1,000,000 times at this point, and that's only a small exaggeration. And then we're going to go and use all 3 of these transformations to get the new graph. So first we shift to the right 2 units. I'm going to do this very quickly. I think at this point we have done enough shifts that you should be able to do this in just one moment by taking each of these points and shifting them to the right 2. Then we need to do a vertical stretch by a factor of 3, which requires a little bit more thought. Each of these points needs to be 3 times as high up, as far away from the x-axis as they started. The one that's on the x-axis isn't going to change, but the other ones will. These 2 points are 1 unit above the x-axis. If we stretch that by a factor of 3, they become 3 units above. And then these 2 points are 4 units above. If we stretch them by a factor of 3, those go up to 12 units above, which is somewhere up here. And we're just going to remember that they're 12 units above for a moment, because when we shift down, we'll be able to actually move them back on. But anyways, these are our points after we've done our vertical stretch. Now we need to shift them all down 4 units. So this point here, when it goes down 4 units, is going to move here. These 2 points, when they shift down 4 units, are going to move here and here. And then these 2 points were at a height of 12. When we shift them down 4 units, that puts them at a height of 8. So they're going to end up being here and here. And so now we have enough points to draw our shifted parabola. And this is the graph of g of x equals 3 times x minus 2 squared minus 4. Now I want to point out here the vertex is at the point 2, negative 4, and we can actually see where this came from in our equation. The 2 came from the x minus 2, because the h coordinate is the number that's getting subtracted from x, and then the negative 4 comes from the constant term, that is negative 4 in this case. So this matches exactly what we had before. All right. The vertical stretch doesn't actually end up changing the vertex. It doesn't affect that. So that doesn't end up mattering. It's really these shifts that end up choosing where the vertex goes. And so that is why we can read what the vertex is just by looking at the standard form of the graph, of the equation.